Welcome to the video for part 2 of project 9 on throwing an object. So what you see before you is going to be hopefully the finished product from what you get. Obviously this blue curve or parabola represents the object being thrown. It's going to be different for every one of you, but the whole premise is that we're hopefully going to get this kind of result at the end. Colors don't have to match exactly, but totally up to you how you want to approach this. Again, a lot of flexibility. The whole premise is that we can drag this point here along the parametric equations we have, which effectively represent the velocities in the horizontal and the vertical components. Combined together, we can now then produce what we call here the vectors. So what we'll notice here is that we have a vector going out this way. We have a vector going down as well, which we can always transit this over to the point itself where there's the gravity force pulling it down and how much force is actually pulling it down at, and then the resultant vector of the two. When you add those two vectors, you get this resultant vector right here. So how on earth do we create this? Luckily for us, Desmos can do a lot of the heavy lifting. However, you as the user needs to be the one who, not codes this, sorry, not computer science. You're the one who has to write the equations to create these here. So you can clearly see there's a line going here, and it seems like at a single point, this line kind of like only touches it once, maybe like a tangent line? Hint, hint, maybe? Maybe a direct or indirect notion of the calculus concepts you guys will learn towards the end of quarter 4 / also the entirety of next year in calculus, either in A, B, or BC. And then we have the horizontal component, and then we got the vertical component. So trying to get all these in is going to be a little tricky, but we realize this is just a horizontal line, so y equals something. This is a vertical line, x equals something. And what those values are depend on the context. So let's try doing this into our own separate things here. So what we're first going to do is we're going to have the two parametric equations. So the way I'm going to type it is I'm going to say x1. I literally just type x1. It does it for you. But in case you want to force it to be a sub, you can do the underscore. So shift dash and then 1. Put the parentheses. We're going to say in terms of t equals something. Again, yours is going to be specific to your case. I'm just going to keep it simple and just do something like this. Again, yours is not going to look as pretty as this, but for demonstration purposes only, I'm keeping it simple. Then we'll do the same thing for the y1. And we'll just do something like this. I'm just making numbers up as we go here. I guess we'll do that, and sure, why not? Okay. These we don't really care too much about, so we're going to just take these off. If you want to explore with these later, what they look like visually on the graph, you're more than welcome to. But what we're trying to do is how do we graph these parametric equations as parametric? Because right now Desmos thinks it's a linear function. That's not what we want. So the way we go about it is we have to create a coordinate point of these parametric equations, and then Desmos will be like, oh, I see what you want to do now. Now you give a set of parameters of how far we go in terms of t. In this case, t represents time. So let's just go for like, I don't know, 2 seconds. We can see, okay, that's around 2 seconds. We'll just keep going 3. And that seems like a pretty good amount. All we care about is the ball's thrown up. We'll just assume it's a ball. It's thrown up, hits the vertex or apex, however you want to call it, and it comes back down and hits the ground here at this point here. Okay, so this is cool and all, but that's not the point of parametrics that's really important. It's the next part here, where we say the exact same statement as row 3. The only difference now is I change this to A. Now the reason why I change this to A is that I can create a slider from which I can now drag the point along the curve. So if I put A represents the time. It's an actual value for time. So in this case, the value for time is 1. It's saying at exactly 1 second, the ball's here. So we're going to change the time constraints a little bit because we know it's around 3 seconds in steps. Let's just keep it real small. Let's go with that. And so what happens now is as I drag this point here, I can either do it on the slider or I can do it on here in the graph. We'll just do it in the slider so you guys can see visually speaking here. We'll say time equals 0, right there, 0, 5. As time goes on, we can see what happens. Ball goes up, slows down, and then gains speed and accelerates down that way. You can drag the point like so. And if you want a more fun way of Desmos doing it for you, you can hit the play button. It can show you exactly the trajectory and speed at which it's going. And then it goes backwards just to reset the whole pattern. And folks, there you go. That's pretty much it. Now, this is the easy part, unfortunately, just playing about the syntax, figuring out how does Desmos do everything parametrically. Now we have to combine the idea of the vector into this whole component. So the question is, how do we get the velocity vector? It's the vector that's kind of like tangent to this point, and it was like kind of protruding out in that direction. So we know like if the ball's like here, we freeze time, or we imagine that we teleport ourselves into space, the ball is going to continue to go forever in this general direction. The question is, how do you figure out exactly what that direction is? Well, the way we're going about this is we're going to cheat a little bit, and we're going to use a calculus concept called the derivative. All you need to know for right now is that the derivative represents the slope of the tangent line. So if I go back to the example that I showed you guys at the beginning, the full-fledged out one, you see that this green line here is tangent to this point right there. And so the derivative allows us to find the slope of this specific tangent line. Unfortunately, that's not the entire story because, yeah, the slope is great and all, but it doesn't tell us exactly where we need to put this line. So I'll show you guys in a second what that means. So what we'll do here is we'll create an equation to represent that vector. And again, we want to create that velocity vector here. And I'm going to move this up because this will come into play in a minute here. So we want that velocity vector to go out like that. Okay, so let's just call it v and then we'll just say the velocity, something like that. So v velocity, I'm going to say is equal to, and this is where now we need to create the equation. So how do we get the slope of that particular tangent line? Well, the way we go about it is we take the derivative of that part right there. And so what we need to figure out is how do we find the slope of this part right here? And then afterwards, take the derivative of that. So first thing order of business you figure out is how do you find the slope of this right here? And let me remind you that the slope, put a little expression here. Let's put a little note. So remember, the slope is equal to the rate of change of y divided by the rate of change of x. So if I kind of group this all together here, just so you get an idea. Hopefully this you recall from Algebra 1 the idea of slope. Rise over run. The change of y over the change of x. Hopefully we know what y is based on some concept from up here, and we know what x is based on some concept up here. And so if it's saying it's the rate of change of y, this is also what we call the derivative of y. You can also say the rate of change of x, the derivative of x. Just so that you're clear of how you write this, the way you would write the derivative of y, you say y, and then you put the apostrophe in front of it. Now, if we're trying to just strictly show just the derivative of the x component, which in this case would be x sub 1, you say x sub 1 and then put the prime afterwards. We'll put t just so we have that. And so what this tells us is that for this particular function of x sub 1 of t, so this function right here, the simple one where it's just 10 times t, it's saying that the derivative, so as I apply the prime here, the derivative of x of t is 10. And so we can kind of use this concept, and again, we're trying to find what the slope is. So if I use the whole y equals mx plus b, because that's really what the tangent line was, it's y equals mx plus b, you gotta figure out what m is, you gotta figure out what b is, all that jazz. What we need to figure out is what m is, and as I mentioned to you before, the concept of m, the slope, is the change of y over the change of x. Remember, you have y, you have x, but you want the rate of change of y, the derivative of y, and then the rate of change of x, or the derivative of x. Hopefully it helps a little bit here. Now, to help you out with this part, what we do need to mention is that there is going to be a little trick we got to do here, where we say something like this, and maybe this rings a bell from, back maybe in, say, in Algebra 2, when you were about translating on the vertex form, so to speak. So we're just writing this in vertex form just for a linear function rather than for a quadratic. But if I go ahead and create some quick sliders here, we find that this is what we got here. This is the linear line. And we're going to try to potentially change the slope, kind of like that, change the h and the height, so we get something like this. And so we can visually see what's going on here. Now, the reason we do need this shift is you'll see as this slider moves, I need the tangent line to be able to move with the point itself. So if this point here is at 10, right? So we can see x is 10, the point here is at 10. I need to make sure the line is also at 10 as well. So that's what this minus h is for. It's to help move it over so that it matches with that. So the question for you all is to figure out what is this h going to actually represent. So in this case, I think I gave you enough hints for the m, so I think this one I might be able to just do for you guys, just so you're aware. But for the h here, how much you move over is going to be basically, it's how much over to the right I have moved. Well, which function here represents how far over to the right you've gone? Is it the x parameter or is it the y parameter? And hopefully this gives you a hint of which parameter it's going to probably be. Very likely the x parameter. So if I move it over by x sub 1 of, in this specific case, we might go with a, because again, a is sort of our time. This is like where everything is dependent on. This gives us an actual value. And so what we now see is we see, again, the slope is incorrect because like we're saying the slope is this, right? And the slope changes as time goes on. And you guys will have that eventually. But we're saying that as the time moves on, notice how the line moves with it. And we got a couple more things we got to fix here. And the last thing we got to fix is the h, the height. And hopefully that tells you kind of where our starting point is. And maybe, just maybe, something in your equations here gives you the height of the function itself. Okay, so let's just say, I'm going to say the height. I can just move this up a little bit just so I feel like, okay, bam, there we go. And so as I move the time slider now, we see more and more. We get closer and closer as everything shifts accordingly. So what ends up happening is you should see something a bit more akin to this here. So I wish I could change color there, but we're not going to show that yet. So we're going to have something like this. Now, had you had the correct slope and everything else included, you would have something like what I have here. Now, one more caveat we need to definitely address is the fact that as you're moving it, right, the whole line is being shown because we said the domain is all real numbers. And the way we can change that is we can use these curly brackets here and say, okay, what is the domain actually going to be? How do we figure out what that is on this part right here? And the way we're going to go about that, and just to make sure we're set, actually, I think I should just give you guys h because I think seeing the h move with it is going to be helpful because h is not just 5 or wherever we started here. I said it was 5 at the beginning, but it changes. It's going to represent the height of the function at any point in time. So the height of this part, so the y value of this part, or in other words, the y value of that part. Okay, hopefully this helps a little bit now, just a bit more. Yep, there we go. Okay, so slope is obviously not changing because we didn't have the right slope, but I'm going to let you guys, do that on your own. But we can see that the whole function now applies. Now, we got to fix the domain and figure out that we only want to start from this point right here, or I guess the x value here, and we only want to go as far as this vector is supposed to go. So the way we can easily go about that is we can say something like this. We can say, okay, I'm going to start from this point right here, and we know how we do that because we kind of use this concept from before we shifted to the right. Apply that. Less than x, that's the domain. Okay, so we got, ooh, interesting. So as I move in now we have everything starting from there. And somehow we need to only have the vector here, the velocity vector, only go over as big as it is. Recall, the velocity vector is going out at a certain magnitude from this point here. So for example, from this point right here, right, we notice that the velocity vector is going to probably be flat like this. It's going straight like that because it's a curve, it's going to come back down, so it's going to go straight like that. The velocity vector has to go out a certain amount. So let's just put it right here. We'll just change m to help us out a little bit. Okay, m is probably something like that, more or less. I'm just guessing, just in case here. We need to go out a certain amount. And so we remember the velocity vector is simply just the horizontal vector and the vertical vector, right? So there's a horizontal coming here, a vertical coming here. We kind of create this triangle. So this part only goes out as far as the x will go out for. So how do we do that? Well, we need to take, this is the minimum value. We already got it, x sub 1 of a. And then the second part, we're going to say it's going to be contained by x sub 1 of a plus a certain amount. So if we do like plus 5, you can kind of see as it goes out, velocity vectors like that. The problem is the velocity is not always going to be 5. And that's what you're assuming in this particular case here by saying x sub a plus 5, or 4 in this case. It doesn't really matter what the number is. So how do you figure out how far the velocity vector is? Well, we do know how much the velocity vector is going to be by utilizing the derivative. So if you use x sub 1 prime of a, meaning the derivative of a, that effectively would tell you how far out you need to go. It's going to tell you the size of that vector, so to speak, or the magnitude of the vector. Again, this is the horizontal component, but because we're using the resultant vector or the velocity vector, it's going to tell us how far out we go, and so that's going to map. And hopefully we can kind of see the triangle produced here. So when we put this all together, you can kind of see it's rolling out and basically doing the same thing that we need to do. Visually, nothing changes because, again, m is not fixed. We have it fixed here. Remember, for your case, it's not going to be fixed, so keep that in mind. But if we see the true case here, and we go from here, we go out, we can see, yes, the velocity vector does change as here. We can see that it gets completely horizontal and then keeps going down. Hopefully we kind of see that there's a triangle going on here. Now, what I'm going to do is I'm going to already give you the horizontal just so you guys can see what's going on as I go from here. So if I zoom out a little bit, we can see, yes, we can almost create a triangle coming out from this, and no matter what, I can always create that triangle from there. Lovely. All right. Now comes the hard part. In case that wasn't the hard part, you're like, wait, excuse me, what? Yes, there is another part to it. So I'm going to come down over here. And what we need to do now is create the vertical vector. Again, it seems easy. It's just like x equals something, right? Unfortunately, that's not going to be the case when things turn negative. It's easy when it's positive, but when we turn negative, we're going to do some piecewise shenanigans here. And piecewise, we can do it in a couple different ways. So first, we'll worry about just trying to get the positive portion of it to work, and then we'll worry about the negative portion. Clearly, at the very beginning, we can clearly tell that the vertical vector is going north or up, positive, right? We don't have to worry about negative too much. So if I want to go up, what I need to do is I need to go out to where the horizontal component ended and go straight up to where the vertical component meets the resultant vector or the velocity vector. So how should we start going about doing that? Well, I can find the end here because all I know is that it's just going to be wherever the point is. So wherever this point is, x of a, and then it's going to be the magnitude, or x prime, the derivative. That's the size of this guy. So x prime. Okay, so that's easy. That's just going to be x sub 1 of a plus x sub 1 prime of a. And that gives us exactly the line we need. So when you move this around now, you can see, hey, lovely. Unfortunately, that is also the easy part. Now comes the fun part, or maybe the hard part, or both. So the way we need to go about this, we need to restrict it so that it goes from here to here. So you'd be like, oh, easy, easy. Obviously, we just need to make sure it goes from the y value down here to the y value up here. Or in other words, the y value of this part to the top of the y value right there. Hopefully you catch my drift about maybe the same component here, the same concept, it's just with the y values. So in other words, we're going to do y sub 1 of a less than y in this case, because we want to go up. So it's going to say that nothing lower than the point here is going to show, but we want to cap it up right there. So hopefully this same concept here is going to apply with what you're doing there. This one I'll probably give to you because the next one is going to be the one I will let you guys do on your own. So I'm going to add the y1 prime of a. And there we go. Seems like we're on business, right? It seems like everything's great, everything's awesome. And then this happens. And the reason why this happens is because when you get the derivative to be negative, you got to remember, when you have a negative derivative here, right there, that means that this right side of the inequality is smaller than the left side. And as you know, in the compound, it's smaller on the left side, bigger on the right side. This logically does not make sense. So what you need to do is you need to make a piecewise for the flipped scenario, where this, the y1 of a plus the derivative of y of a, this is on that side, and then this ends up being on the positive side. So the way we go about this is, because we have quite a few conditions here, what we're going to do is we're going to make a giant piecewise function. And I apologize, there's no real good visual way to go about this, so just bear with me here. We're going to make a giant piecewise function. And so we cap everything inside of the curly braces here. And what you're going to do is you need a condition first. You're going to say, for a specific condition, have this function shown on the graph with this parameter thrown in. So we can keep this exactly the same. All I'm going to say is, what causes this part to show on the graph? Well, we can see visually speaking, okay, it shows as in, where'd it go? Of course, I'm not finished with this yet. Let me just double check. I think I got everything here. Do I need to have a condition? Yeah, I need a condition, that's why. Okay, so we're just going to put some stupid condition here. We're just going to say, for x is bigger than 0, we're just going to do this. So the way we go about it is you're saying this condition, if x is greater than 0, then create the function here. So this is not entirely true, but you'll see in a second why this is important. So let's just go through it. We know that the vertical velocity vector is shown until something changes. And hopefully this reminds you about the derivative concept. The derivative of derivative of the function here, so this part, the velocity function, is represented by the vertical component. It's the magnitude of the vertical component. This is positive, right? But this derivative is becoming positive. Derivative of the y component is positive. As I go there, the moment the derivative becomes negative, that's when we need to do a flip. So the condition here is that the derivative of the y component, so derivative of y, we go like that, has to be greater than 0. I think I need to include that it's going to be at the a component, at the a component, yeah, for that part right there. So then if we come back, we can see that for the piecewise function, the piecewise function will apply only when it's positive. As soon as it hits negative, watch what happens down in row 10. Boom, it says x is undefined, because we didn't define when the y, or the derivative of y, is negative, what happens then. So now that we have that, what you can do is, this is the first condition and the first piecewise function. After all of this, and I know it's lengthy, so bear with me on that, this is the end of the piecewise, and this is the end of the range, or the domain that we put for that first function. You put a comma, and then you enter in the second equation. So you need to put a condition, so when the derivative is negative, colon, do the next part right there. That's pretty much all you need for the y component to get effectively what is on this side right here. And then once you have that set to go, I leave the rest to you with the horizontal component, because the horizontal component really is just, again, a lot of the stuff I told you about the velocity component, or the velocity vector, just applied only in the horizontal context. Another way to think about it is you can take the vertical component that you have constructed, or partially constructed here, and maybe just take that whole thing, copy and paste, and just tweak a couple things around, because they're basically the same thing, just different perspectives. Hint, hint. So hopefully this helps a little bit about constructing everything here. Again, I know that this video is going to be, it's going to feel like it's pretty long. There's a lot of components thrown in. You're like, what's a derivative, right? And all that matters is as long as you have the base definitions down and you can see what's going on here, we're trying to create a visual to help us better understand velocities within the context of the parametric function here. So I think aside from that, we should be all set to go. Again, use this graph to your benefit. Once you have this, again, I feel like part 3 is going to be so much easier to visualize and help you out as you mess and tinker around with this stuff. Recall, as you get to part 3, we have the first parametric equations denoted by x sub 1 and y sub 1. You can create an infinite number of these. So you can do x sub 2, y sub 2 for object number 2. Continue this on pattern forever and ever. So hopefully this helps a little bit, at least provide some context and get you started here. I did leave a couple of gaps there, but I'm explaining just more or less what's going on with the screen, just so that you get this idea here. So take your time with it, breathe, it's okay, and it's totally fine that we still don't know what the derivative is. Again, all we said was it was the rate of change, or the slope, of the tangent line at a particular point. That's all that matters at this point in time. You should be set to go.